Dear students, today our topic of discussion is electric flux. It is the total number of electric field lines passing normally through a surface. To know more details about electric flux, we need to know what is area vector. The vector of a plane surface whose magnitude is the area of the figure and whose direction is that of a perpendicular to the plane of the figure. Now if you see this, here it is a rectangular surface, and for this rectangular surface this is the area vector. You can see the direction of area vector which is perpendicular to the surface, and you can find the magnitude of the area vector just by multiplying length and breadth of this rectangular surface. Now let us see these figures. Now for these figures, you see the black dotted line indicates the area vector, and in all these three figures you can see that this area vector is perpendicular to the surface. These red lines indicates electric field lines passing through that surface. Now only for the first figure you can see that electric field lines are normal to the surface. Fine, electric field lines are passing normal through that surface. So if you see this first figure again, now can we look for the component of E which is parallel to A, because according to the definition of electric flux, it is the total number of electric field lines passing normally through that surface. So we have to look for the component of E um, which is parallel to the area vector. So definitely it is E cos theta. E cos theta component of E is parallel to the area vector. Okay, so can we write flux as phi is equal to E cos theta into A, or it is EA cos theta, or we can write it as E dot A, because we have already learned dot product in class 11 standard. So let us see the mathematical expression for electric flux. Phi is equal to E dot A, so EA cos theta. Now if you want to calculate flux link with these surfaces, you see these surfaces are at different orientations. Now for the first surface, you see theta is equal to 0. The angle between electric field and the area vector is 0. So maximum flux is linked with that surface. You see all electric field lines are passing normally through that surface. So maximum flux is linked. So the value of maximum flux is EA. Similarly, for the second surface also, if you know the angle theta, that is the angle between the area vector and the electric field direction, you can calculate the flux link with the second surface. Similarly, if you see for the third surface, the angle between the electric field vector and the area vector is 90°. So flux link with the surface is 0, because if you use this expression for flux, phi is equal to EA cos 90, so it is 0. That means the flux link with the third surface is 0. SI unit of electric flux, you can see it is Newton per Coulomb um, into meter square. For electric field it is Newton per Coulomb. For area it is meter square. So Newton Coulomb inverse meter square, and it is a scalar because it is just a number. Let us practice some problems on electric flux. Let us see this example 57. If E is equal to 6I plus 3J plus 4K, calculate the electric flux through a surface of area 20 units in YZ plane. So you see it is YZ plane you have to. So the direction of electric value of electric field is given. E is equal to 6I plus 3J plus 4K. So what you need is area vector. So area vector if you want to draw on the YZ plane, so definitely the area vector should be perpendicular to the YZ plane. So if you draw a area vector which is perpendicular to the YZ plane, definitely it points along the direction of X. So that is why I have to put area vector A is equal to 20I. Fine, area vector A is equal to 20I, because area vector has to be perpendicular to the surface, and here the surface is YZ plane. So if you want to draw a normal on the YZ plane, definitely that should be parallel to the x-axis. Fine. So it is 20 I cap. Okay, 20 I cap. So you use the formula flux is equal to E dot S. E dot S, use the properties of dot product, so you will get the answer as 120 units. Next you see a circular plane sheet of radius 10 centimeter is placed in a uniform electric field of 5 into 10 to the power 5 Newton per coulomb, making an angle of 60 degree with the field. Calculate electric flux through the sheet. Now you see again we have to use phi is equal to ES cos theta. But what is theta? Theta is the angle between the area vector and the electric field. But here what is given? The angle given here is the angle between the electric field, direction of electric field and the plane sheet. But you have to find the angle between area vector and the electric field vector. So definitely the angle between area vector and the electric field vector is 90 minus 60 is equal to 30 degrees. So here you have to put ES cos theta. ES, it is a circular surface, so that is why pi r square. Surface area you can see pi r square, and cos 30 degree. Accordingly you will get this result 1.36 into 10 to the power 4 Newton meter square coulomb inverse. Okay. Next you can see a cylinder is placed in a uniform electric field E with its axis parallel to the field, so that the total electric flux through the cylinder is 0. Now if you see this cylinder, you can see there are three surfaces, mainly these are the two end surfaces. This is 1, you can say this is 2, and this is 3, this curved surface. Now if you consider any surface element, small surface on these surfaces, say example you consider this surface ds. Now on this surface if you draw the area vector, the area vector is parallel to the electric field, because you see electric field is along the axis of the cylinder. It is already mentioned that direction of electric field is parallel to the axis. Okay, you can see this electric field E with its axis parallel to the field. So I am considering that direction of electric field is this. So for this surface, the angle between the electric field and the area vector is 0. For this surface, you see, if you consider a surface element here, for this surface, the angle between the area vector, this is the area vector, this is the electric field, the angle is 90 degree, sorry, 180 degree. And here for this curved surface, you see the angle between the area vector and the electric field, it is 90 degree. So this surface has no contribution to the flux, total flux, because you have got flux is equal to E dot A or E dot S. If the angle is 90 degree, then flux will be 0. So this curved surface has no contribution to the total flux. So how can I write flux through the entire cylinder? You see total flux is equal to integration E dot ds left face plus integration E dot ds right face plus E dot ds curve 1. Now I want to tell you the meaning of this. If you want to write the, let us consider this small surface. If you want to write the expression for flux link with this small surface, it is E dot ds. But if you want to write an expression for flux link with the whole end surface, then I have to write integration E dot ds. So that is the meaning of this. Similarly, this small surface, if you want to imagine a very small surface there on the whole curved surface of the cylinder, and also if you want to write the expression for flux link with that small surface, it is E dot ds. But if you want to write an expression for flux link with the whole curved surface of the cylinder, it becomes integration E dot ds. Fine. So it is like this. Now you see for the first phase, for this left phase, you see the angle is 180 degree, so integration E ds cos 180 degree. for this phase it is E ds cos 0, and for this it is E ds cos 90. So you see the result is 0. For this you see area it is pi r square. So total uh, flux through the entire cylinder is 0. Next you can see you see this, the electric field components in figure 1.88 are Ex is equal to alpha x to the power half, Ey is equal to Ez is equal to 0, in which alpha is equal to 800 Newton per coulomb meter square. Calculate the flux through the cube. Okay, now you see the cube is placed here. You see the coordinate system fixed here. This is the origin of the coordinate system. Now we'll see flux link with this phase. Okay, this phase and flux link with this phase, because these other phases they are not going to contribute to the flux, because for the other phases the angle between the electric field vector and the area vector is 90°. So only these two phases contribute to the flux. So let us take this phase. This is the left phase, so it is written as EL. Okay, electric field for the left phase, this one. So EL is equal to alpha x to the power half. This is the value of electric field. It is already given in the question. E is equal to alpha x to the power half. But what is the value of x for the left phase? That means at what distance this phase is from the origin. This is a. So you put the value a in place of x. So alpha a to the power half. So what is the flux link with that phase? So phi is equal to E dot del s. So E del s cos theta. But what is theta? Direction of electric field is along x-axis, and area vector is opposite to that. So what is the angle? The angle is 180°. Fine. So it is 180°. So it is minus E a square. Similarly, for second phase also you can see at what distance this phase is. It is at a distance twice a, here to here a, here to here a, here to here a. So it is twice a. This phase is at a distance twice a from the origin. So in place of x we have to put twice a for this right phase. Okay, so you see here ER is equal to alpha x to the power half. You can see, so alpha in place of x it is twice a to the power half, and phi you see E del s cos 0, it is 0. For the second phase it is 0, because this is the direction of electric field also, and if you want to draw a surface vector on the or area vector on the surface, it will be parallel to the electric field. So angle is 0, so it is cos 0. You can say cos 0, that is cos 0. So total flux phi is equal to phi l plus phi r. You just simplify this, you will get 1.05 Newton meter square coulomb inverse. Fine. The last one you see, an electric field is uniform and in the positive x direction for positive x, and uniform with the same magnitude in the negative x direction for negative x. It is given the value of electric field is given 200 I cap when x is greater than 0. That means this part, x is greater than 0 means this part, and E is equal to minus 200 I cap Newton per coulomb for x is less than 0. That means this part. Here also you have to do the same thing. Now if you draw this area vector, you see for this surface the direction of electric field, this is the direction of area vector. For this surface you see this is the direction of electric field. Of course it is negative x-axis, so we have to put E is equal to minus 200 I cap. So I cap is the unit vector for positive x-axis, so minus I cap is the unit vector for the negative x-axis. And definitely we have already learned that this curved surface is not going to contribute to the total flux. So let us see on the left face, that means for this E is equal to minus 200 I cap, del s is equal to minus del s I cap. Clear? Area vector you see along x-axis I cap, Along negative x-axis is definitely it will be minus I cap, so it is minus del s I cap. So total flux, you see, flux linked with that left phase, the outward flux through the left phase is phi is equal to E dot del s, so you will get 1.57. Similarly on the right phase, E is equal to 200 I cap, because it is along the positive x-axis. Del s is equal to del s I cap along the positive x-axis. Both are parallel, angle is 0, so that is why phi is equal to E dot del s, so it gives you 1.57 Newton meter square Coulomb inverse. And for the curved surface, you see, it is not going to contribute to the flux because E is perpendicular to the del s. So if you consider any small surface here, surface element here, and if you draw the area vector and the electric field, you see this, it is 90°. The angle between area vector and the electric field is 90°. So this curved surface is not going to contribute to the flux. So total flux, you can add all these three. 1.57 due to the left flat surface, 1.57 due to the right flat surface, and 0 for the curved surface. So total is 3.14.